Welcome to lecture 11 on measure and integration. In the previous lecture, we had defined what is called a outer measurable subset, and we had started looking at the properties of the outer measurable sets. We will continue that study of properties of the outer measurable sets today, and if time permits, in the end we will specialize the case when this space is the real line. So, let us recall what we have been doing. So, properties of measurable sets we were looking at. Let us just recall what is a outer measurable set. A subset E of x was said to be outer measurable or mu star measurable if mu star of any set y is can be written as mu star of y intersection E plus mu star of y intersection E complement. So, this condition must be satisfied for every subset y of x. And then we said let us denote by S star the class of all mu star measurable sets, and we gave a equivalent way of verifying when a set is outer measurable. So, the condition is that a set E is measurable if and only if for every subset y in x with mu star of y finite, we have the condition that mu star of y is bigger than or equal to mu star of y intersection E plus mu star of y intersection E complement. So, instead of just saying that for every subset y this equality must be true, we have to only verify for those subsets y of x for which mu star of y is finite, and instead of equality we have to verify only bigger than or equal to one way inequality, because the other way around is always true for mu star being countably subadditive. So, this condition we will use whenever we required, and so the first observation that we proved last time was that A is the given algebra on which the measure is defined. So, the first claim we proved that every element in the algebra is also a measurable set. So, A is a subset of S star. The second property that we were looking at was that if S star is S star is an algebra of subsets of x and mu star restricted to S star is finitely additive. We had already observed that a set E is measurable if and only if its complement is measurable. So, S star is closed under complements, only we have to verify that it is closed under unions, and that proof we were working out in the last time, and we had done it. Let us just revise it again, because we are going to need those inequalities. So, let us take let E 1 and E 2 be measurable sets to show that E 1 union E 2 is measurable. So, E 1 measurable implies that for every subset y contained in x, and let us also have that special condition less than finite, we know that mu star of y is equal to mu star of y intersection E 1 plus mu star of y intersection E 2 E 1 complement. This is true for every subset y with that property. Let us replace y by y intersection E 1 intersection E 1 union E 2. So, replace this y. So, then we get, so then what we have? We have mu star of y intersection E 1 union E 2 is equal to. So, y is replaced by y intersection E 1 union E 2, but E 1 is a subset of it. So, the first term is just mu star of y intersection E 1 plus the second term becomes mu star of E 1 union E 2 intersection E 1 complement. The first term will give you only empty set union y intersection E 2 intersection E 1 complement. So, E 1 complement intersection E 2. So, that is what we get by using the fact that E 1 is measurable. Also, E 2 is measurable So, thus for every set y, a corresponding equation holds for E 2 complement, but we will replace y by y intersection E 1. So, mu star of y intersection E 1 complement is equal to mu star of y intersection E 1 complement intersection E 2 plus mu star of y intersection E 1 complement intersection E 2 complement. So, using the fact that E 2 is measurable, we have written mu star of y intersection E 1 as the set intersection E 2, the set intersection E 2 complement. Now, so in these two equations, look at this set, this term y intersection E 1 complement intersection E 2, that is also sitting here. So, we will compute the value of this and put it in that equation. So, let us do that. So, from this second equation, we put the value there. So, we have got, so from these two equations. So, thus mu star of y intersection E 1 union E 2, that is the left hand side of this equation, that is the left hand side of this equation. So, that is equal to the first term. So, that is mu star of y intersection E 1 plus the y intersection E 1 complement intersection E 2 is equal to mu star of y intersection E 1 minus that thing. So, mu star of y intersection E 1 complement minus mu star of y intersection E 1 complement intersection E 2 complement. And now, one should note here that we have taken one term on the other side. So, this is possible because all the sets involved have finite outer measure. So, this is the equation of real numbers. So, we can take one term on the other side and so on. In general, that will not be possible if one of the terms is equal to plus infinity. So, the condition that mu star of y is finite is being used here. So, we get, using the fact that E 1 and E 2 are measurable, we get this equation. So, from here let us take this negative term on the other side. So, implies mu star of y intersection E 1 union E 2 plus mu star of y intersection E 1 complement intersection E 2 complement is equal to mu star of this term y intersection E 1 and the second term plus mu star of y intersection E 1 complement. And now, using the fact that E 1 is measurable, this is same as mu star of y. So, we have shown that for every subset y with mu star of y finite, its measure mu star of y can be written as mu star of E 1 y intersection E 1 union E 2 plus mu star of y intersection E 1 complement intersection E 2 complement, but note this set is nothing but E 1 union E 2 complement. So, this implies that E 1 union E 2 is measurable. Okay. So, that says E 1 union E 2 is measurable. And now, for the special case, so if E 1 E 2 are disjoint, that means E 1 intersection E 2 is empty set, that is same also implies that E 1 is contained in E 2 complement or E 2 is contained in E 1 complement, either one is true. So, note this is true. So, in that case, let us go back and look at the first equation that we had. We had, because E 1 and E 2 were measurable. So, we had this condition, right. So, in this equation, this is true for every y. So, let us replace this y by E 1 union E 2, that will give us the measure mu star of E 1 union E 2. So, in this we are going to replace y by E 1 union E 2. So, let us just put that equation here and look at what we are doing. So, in this equation we are putting y equal to, so in this star, so in star put y equal to E 1 union E 2. Keep in mind they are disjoint. So, the left hand side will be mu star of E 1 union E 2 equal to right hand side, the first term is mu star of E 1 plus in the second term, because E 1 E 2 are disjoint, E 2 is a subset of E 1 complement. So, this implies E 2 is a subset of E 1 complement. So, that means this is nothing but plus mu star of E 2. E star of E 2. So, when E 1 and E 2 are disjoint, mu star of E 1 union E 2 is mu star of E 1 plus mu star of E 2. So, that means, so thus mu star is finitely additive. So, we have proved that whenever so we have proved this property, namely S star is an algebra of subsets of X and mu star restricted to S star is finitely additive. Next step is to go a bit further, and we want to prove that whenever you got a sequence of sets in S star which are pairwise disjoint, then their union is also in S star, and mu star of the union is equal to summation of mu stars of A n. That means, we are going to show that S star is closed under pairwise disjoint union of sets, even countably infinite, and mu star is countably additive. So, let us prove this property. So, let us take, so A n belong to S star, n equal to 1, 2 and so on, pairwise disjoint. That is, A n intersection A m is empty for n not equal to m. Right. So, we start A 1 belonging to S star, A 1 measurable implies that mu star of any set y can be for every y contained in X. I can write this to be equal to mu star of y intersection A 1 plus mu star of y intersection A 1 complement. And now, use the fact that A 2 is measurable. So, leave the first term as it is, y intersection A 1 plus A 2 is measurable. So, measure of mu star of this set can be written as mu star of A 1 complement intersection A 2 plus mu star of y intersection A 1 complement intersection A 2 complement. So, this term mu star of y intersection A 1 complement is written as mu star of y intersection A 1 complement plus intersection A 2 plus mu star of y intersection A 1 complement intersection A 2 complement. So, here we have used the fact that A 2 is measurable. And now, observe that A 1 and A 2 are disjoint. So, A 2 will be a subset of A 1 complement. So, this set is nothing but y intersection A 2. So, I get this is same as mu star of first term A 1, the second term is mu star of y intersection A 2, and the third term as it is mu star of y intersection A 1 complement intersection A 2 complement. So, in the first we use A 1 is measurable, in the second we use A 2 is measurable, and use A 1 and A 2 are disjoint. We continue this process. If we continue this process, after n steps we will have this is equal to, the second step gives you mu star of y intersection A 1 plus mu star of y intersection A 2. So, after n steps this will have mu star of y intersection A I equal to 1 to n plus one term will be there which is mu star of y intersection a 1 complement intersection up to a n complement, right. So, let us write this last term in terms of union. So, this is equal to summation of I equal to 1 to n mu star of y intersection a I plus mu star of y intersection union a I equal to 1 to n complements, right. So, this term is represented in terms of complements of the unions. So, this is after n steps. So, for every n we have got mu star of y can be written as this. And now, this is true for every n. So, here I would like to write this union as 1 to infinity. If I do that, I will be making this set bigger, and hence the complements will be a smaller set. So, replacing this set. So, if I replace this by y intersection union I equal to 1 to infinity of a I complement, this set is bigger than this smaller than this set. So, mu star of this will be bigger than mu star of this. So, if I write mu star of this, so this term is bigger than this term. So, this will be bigger than or equal to summation I equal to 1 to n, this term as it is y intersection a I plus this. So, what we have done in the second term, where it was union 1 to n, I have taken union 1 to infinity, and because of complements this term will be smaller. So, instead of equality I have got the inequality, and this happens for every n. So, I can let n go to infinity. So, this will be bigger than or equal to summation I equal to 1 to infinity mu star of y intersection a I plus mu star of y intersection union I equal to 1 to infinity a I complements. And now, mu star is countably subadditive. So, this term, the first term is bigger than or equal to mu star of y intersection union a I equal to 1 to infinity, second term as it is. So, mu star of y intersection union 1 to infinity a I's complement. So, using the fact that for every n, a n is a measurable set, we are able to say that mu star of y is bigger than or equal to mu star of y intersection the union a I's plus mu star of y intersection the complement of the unions. So, that implies that union a I 1 to infinity belongs to S star, is a measurable set. Not only that, we can say something more actually. So, let us in this equation, so this equation star, this one, let us put y is equal to, so in star let us put y equal to union of a I's. So, what we will get? So, let us do that substitution and see what do we get. So, in this equation in star, take y equal to union of a I's. Then left hand side is mu star of union a I 1 to infinity is bigger than or equal to summation I equal to 1 to infinity mu star of y is unions of a I's. So, this is just a I plus this is union and this is a complement, that is empty set, mu star of that is equal to 0. So, that is equal to 0. So, what we get is mu star of the union of a I's is bigger than or equal to this. Also, by subadditivity, mu star of the union a I's is less than or equal to summation 1 to infinity mu star of a I's. So, these two imply that mu star is countably additive on S star. So, this is very nice. So, we have got the following property, that if. So, what we have done till now is we have shown that S star as a consequence of all these properties. Now, we can say that S star, the class of all measurable sets, is a sigma algebra of subsets of S of X, and mu star on this is countably additive. So, we started with a measure mu on a algebra A of subsets of a set X. We defined an outer measure via this on all subsets of set X. Then we picked up a subclass, namely S star of sets which are mu star measurable, and we have shown that mu star, which in general is countably subadditive, is actually countably additive on S star, the sigma algebra of measurable sets. So, it is a sigma algebra. Why it is a sigma algebra? Because we have already shown it is an algebra and it is closed under countable disjoint unions. So, any collection, any algebra which is closed under countable disjoint unions is automatically a sigma algebra that we have shown. So, this gives us a way of defining measures on extending measures. Before doing that, let us observe one more thing. Let us look at sets E in X whose outer measure is 0. These are called sets of null outer measurable sets. So, the claim is every set whose outer measure is 0 is automatically measurable. So, let us check that. So, let E be a subset of X and mu star of E equal to 0. Then, for every y contained in X, mu star of y intersection E is equal to 0, because y intersection E is contained in E, and mu. So, because and mu star is monotone. So, this is 0. So, thus mu star of y is bigger than or equal to mu star of y intersection E complement, because again y intersection E complement is a subset of this, and I can add 0 to it. So, that is equal to mu star of y intersection E complement plus mu star of y intersection E, and that is precisely saying that the set E is measurable. So, that shows that the class of mu star null sets are also measurable. So, this class N is inside S star. So, let us summarize the process now what we have gotten. So, let us start, we said that let us start with a measure mu on an algebra. Mu is a measure, A is a algebra of subsets of the set X. Then, if mu is sigma finite, then there exists a unique extension of mu to the sigma algebra generated by it. And how do we conclude that? So, the conclusion for that is as follows. So, mu is on the algebra and it is sigma finite given. So, we define from it outer measure mu star, which is defined on all subsets of X. It is countably subadditive, and we picked up the class of measurable sets S star. So, if we restrict mu to this, so let us call it as mu bar, there is a restriction of mu to the smallest smaller class S star. Keep in mind S star is right the class of measurable sets, and so what is mu star? Mu star mu bar. So, mu bar is equal to mu star restricted to S star. Then this is a measure. S star is a sigma algebra and this is a measure, and we know that this is an extension. So, from mu we come to mu bar, an extension of mu from the algebra to S star, and note A is all sets in A are measurable. So, the sigma algebra is also inside here. So, A is inside S of A, which is inside S star, which is inside all subsets of X. So, mu is defined here, we get mu star here, and we restrict, we get mu bar, and that is same as mu bar on S of A. So, we get a measure mu bar on S of A. So, that is same as mu bar on S of A. So, what is mu bar? Mu bar is the restriction of the outer measure mu star to the sigma algebra generated by A, and that is inside the class of measurable set. So, it is a well defined measure, and because mu is sigma finite, supposing there were another extension by some other method to the sigma algebra, then by the uniqueness of measures on the sigma algebras, we know that there is only one possible extension, that we have already proved, that in case an extension exists, if two measures agree on the algebra, they will also agree on the sigma algebra, provided they are sigma finite. So, uniqueness follows from that theorem. So, we have got that if mu is a sigma finite measure on an algebra, then we can extend it to the sigma algebra generated by it. So, this is the extension process. So, one has to start with a measure mu on an algebra, and recall we already have extended it from a semi algebra to the algebra generated, right. So, essentially it says that if we have a measure on a semi algebra of subsets of a set X, and the measure mu is sigma finite, then it can be uniquely extended to a sigma finite measure on the sigma algebra generated by that algebra. In fact, we have proved something more. So, we have actually shown that not only mu, which is defined on the algebra, extends to S of A, the sigma algebra generated by it, actually it extends to a class S star, which not only includes S of A, it includes also the class of null sets, mu star null sets, sets of outer measure mu 0. So, let us denote the class of the sigma algebra generated by S, the sigma algebra generated by S of A and the null sets by a new name. So, what we are saying is one can show that this S star, the class of all outer measurable sets, which is a sigma algebra, which includes S of A, also it includes N. So, it includes this union. So, this union we are writing it as sets of the type. So, S A union N, it is not the union of these two classes, it denotes sets of the type E union N, where E belongs to S of A and N is a null set. So, take sets which are in the sigma algebra generated by A, adjoin to it any null set, mu star null set. So, look at this new collection, then one can show that S star is same as E union N. So, it involves two things, namely this collection is a sigma algebra and this sigma algebra is same as S star. We will not go into the details of this, they are slightly technical, we will assume this.